I'd probably say this is one of the better virtual conferences that I've been involved with, so that's great. So in terms of the overall methodology discussion, the results that I'll try to cover in the time allowed, most of that just actually was just published in this paper here earlier this year. It is available open access, so certainly take a look and feel free to chime in or ask any questions along the way, or excuse me, at the end, I guess it would be. So in terms of an overall outline, we'll cover a lot of the overall goals of the method. Of course, certainly a lot of this would probably be old hat in the sense that certainly if you're at this conference, you understand why we're trying to do free energy methods, the problems we're trying to solve, and so on and so forth. I will give a brief overview of the theoretical underpinnings, in part because this is a different approach to the problem. It's not an alchemical method. It's not something that we're trying to watch how one ligand changes to the next or do a lot of dynamics. It's another way to solve the problem. We'll go through some examples. And again, those are the examples in that aforementioned paper. And I will just briefly touch on what the overall workflow looks like, because again, it is a little bit different than what most folks would be dealing with when it comes to usual standard free energy methods or alchemical methods. So in terms of the broad strokes, the method itself was licensed from Michigan State University out of Kenny Mers's group. It does utilize a mixture of both a localized sampling and a global sampling. And that's really the key beneficiary of it, where instead of running a whole lot of dynamics, certainly you could take dynamic snapshots. In fact, that's something that we're beginning to experiment with. But another way to generate a set of coordinates or to sample coordinates, we of course go through a standard docking process, and then again do this localized sampling that I'll touch on in a minute. It is high throughput, and that's one of the bigger differentiators, where for the end state calculations, you're talking about 5 seconds, 10 seconds, 20 seconds or so per pose. And that therefore allows us to move a lot quicker down the chain. And then in terms of the ensemble, that is usually something that you can do on multiple compounds per hour. It's actually usually Docker dependent more so than it is the free energy dependent. So it's kind of, I guess you could say, a nice switch on the whole process. Interoperable, primarily all of the work that I'm going to show was done with the docking side was done with Mo. Then of course, we bring in our scoring then for the rest of the process. In principle, you can use other Dockers though as well, which makes it nice. It is something that we can run anything from a conventional cluster, workstation, even your laptop. So you don't even need a really high-end GPU or something like that to get this sort of speed. In terms of the integration, most of what we've done to date has been either command line driven or graphical user interface driven with Mo as being the GUI. So if you have Mo, this is something that effectively plugs into the package. It is something that, as long as you have our software installed, it is something that will run within Mo. And there is a web service version of a lot of this then too. So if you either, again, talking through Mo, it's talking to our web service, or else if you have your own technology or your own platform that you'd like to work through, it is just a JSON API. And the key differentiator, I think, for this audience would be, instead of having to run dynamics calculations, you're not worrying about some of the complications thereof. It is something that you can usually do with a reasonably good Docker. Now, all that being said, garbage in, garbage out is usually the principle of the day, like it is with anything else. And so if you're not talking about very reasonable low energy landscape minima, that's what you're really trying to show with your docking, then at that point, then as with anything else, all bets are off. So in terms of the overall approach and what we're trying to solve, these are orthogonal approaches to the free energy approach. Again, with FEP and alchemical methods being one way, this would be an orthogonal approach to trying to solve that problem. They're both of these sets of approaches, of course, are theoretically complete. They're based on statistical mechanics, very similar potentials in some regards, where we've got an amber-like force field, which can be used, or the GARF for statistical potential, which would be the original that was in a lot of the original papers. And they're both they are ensemble based. And so neither of these methods or these approaches are dealing with just a single set of coordinates. And that again is more indicative of course what is really going on in the body or in the test tube. So where they differ in a lot of ways is where MD requires these very long simulation times, usually something that you're looking at, certainly hours, days, sometimes weeks, depending upon how much sampling you want to do. We're using this combination of blurring or smearing that I'll explain in a second, this localized sampling and docking. And so therefore, again, it tends to be docking dependent. So just to explain what we're trying to accomplish again schematically, if you think about in the ideal world, and that would be where if we could all do had effectively infinite time, or maybe a bunch of quantum computers at our disposal, in the ideal world we'd be able to sample an entire energy surface. But of course we know we can't really do that, or we can't do that practically. Certainly from an industrial drug discovery process, it becomes very difficult. And so instead, we try to mimic that, or we try to model that approach. And that's where, again, along this left side here, would be these conventional molecular dynamics methods, where you're going to sample, generally you're going to sample more valleys than peaks. You're going to end up in certainly very deep valleys, so on and so forth. But that is what what we can do, or what we can do efficiently in a deployable manner. What instead, the way that this localized sampling works is, instead of doing again a single set of coordinates, or a single XYZ coordinates out to a PDB having three decimal places or whatever, instead what we try to do is we look at every one of these atoms as smeared. And so we're not looking at a single set of coordinates, we're looking at a whole set of coordinates for each atom. And this is done and based on a fundamental assumption of the method that every protein ligand interaction could be decomposed into a pairwise atom type to atom type interaction. And you can think of this really as analogous to if you think of an Amber potential, or if you think of the GARF potential, or whatever potential you're doing. Every atom to every atom is one type to another type. We can then say this energy profile between those two atoms is dependent upon distance, or R between those points. And so mathematically, you could think of it as, again, each one of those points, atom type A to atom type A, just using as an example, maybe this 3.6 angstroms. That's where in the coordinates in the PDB file, it'd be 3.6 angstroms across. And if you think about a Leonard-Jones potential, for example, it would just be simply that distance. Well, instead of doing a single distance, we'll calculate a bunch of distances. And what we do is we generally smear it about a half an angstrom in one direction and a half an angstrom in another. And that creates this nice vector right here, where we're looking at, in this case, we might be looking at 200 individual energy calculations instead of a single energy calculation. These all come together for the partition function, and then finally the Helmholtz free energy. And then from there, we now are mimicking, or we can visualize this as, instead of a single coordinate, we're looking at a bunch of coordinates, a smeared coordinate, I should say. And this entire calculation for a single pose, or a single ligand pose, for maybe an end state calculation, or a set of poses for an ensemble calculation, is measured in approximately CPU seconds, making it very tractable. When we combine that single pose, and again, that might be an X-ray pose, it could be a single pose from a docking run, it could just be simply a single placement that we've tried. We can then pair that together with the docking function. And again, I could be doing this with Mo, I could be doing this with MT doc itself. We could likely do this with Glide or anything else, where we take this as end conformations, or end poses within that active site. We then bring that all together, and instead of doing a single delta G calculation, we're going to do we will bring all of these poses together for that delta G calculation. So now, instead of doing a localized, or excuse me, a single position, or maybe an MD calculation, where again we're exploring just valleys instead of very many peaks. Now we can look at it, if you want to think about it again schematically, where along this right side here, you've got each one of these black points is a is a single pose, maybe from again from a docking run. There are about 25 here, which is our default run. And then each one of those red points there then is where it's being smeared in each direction. And I should note that we're actually smearing not just the ligand side, but also the protein side itself or as well. So you'll get a lot of localized smearing in both directions. And this allows us then to explore a much more significant part of the space. So when we start talking about the workflow, and in this part of the talk, I'll touch on both the MOE-based workflow, which is very similar to or akin to what Max was talking about a few days ago. It uses a lot of those underlying technologies, and then I'll go through a set of results then that were calculated both in terms of a standard set from the PDB-bind database, and then also an additional homologous set then on top of that. So this, I asked Max to provide this slide because I think it's a good overall rundown where again, these are all the tasks that are very similar. Now we have a little bit different in the sense that since we're not doing Amber TI, we don't require all of these dynamics calculations. All of the other steps, though, are very similar. You can use those steps effectively right out of the box. So you'd go through, you have to read the PDB file, you have to generate any missing side chains, backbones, that sort of thing. Again, garbage in, garbage out. If a structure isn't properly prepared, it doesn't matter how fast the calculation is. If you're going to give it a poor set, you're going to get what you pay for, as it were. And so if you go through, read PDB for protonation, of course, neutralization, not required, but something certainly you can do, so on and so forth. And of course, then this ligand positioning, which is the key aspect that we require. So again, having a single set of coordinates, we want to have as many coordinates as we possibly can as our starting points. And so again, showing this as from a GUI perspective, it's a little different than what Max was showing, in part because you can do a lot of this in real time. And so interestingly enough, if you look at everything from approximately this line over to the left here, the viewer is very similar to what any Mo user would see. So that is the standard Mo builder. It's the standard Mo visualizer. Where then along the right side here, that's where we've added in this tool tray, or this piece that is added in as an additional feature. And so again, when you start up Mo, you would load this up and you'd be able to see this, where you can go down through and you can actually make these changes in real time in the builder, and then finally hit run or hit score in order to get that score returned back to your interface. And you could then make another change, so on and so forth. This is broken down a little bit better where, again, if I just zoom in on that one side, the web service itself is what's being talked to. That's the piece that is effectively doing all the calculations. You can also run it locally if you like. Status report saying whether or not you're ready to run or ready to calculate, so on and so forth. This third bullet point is an interesting one, because that one actually is, again, it's effectively calling the Mo-based toolkit in order to do that preparation and to do that run. The a standard MDB or project file, so everything gets loaded into there and is then stored. And again, these are the storing of the ideas, and so you could literally do this in real time at a project meeting or so on and so forth. Choice of potential, certainly what input you want to do, whether it's coming from Mo or an SDF, so on and so forth. And then the key point then here is that once you've brought this in, you could either do this as optimize the structure, optimize the ligand, optimize the pocket, or even just redock the compound within the active site. And then finally, this is all listed out and stored. And so then this would be something that then you could save from one run to the next. Okay. So enough of the technology demonstration. Let's talk about what's going on underneath. And so if you think about the workflow that I'm going to show here in just a second, or I should say the results of the workflow I'm going to run here in a second, it's what everybody would likely expect to see. You have a prepared target PDB file. placed mol2 file, that forms your input. And then at each one of these steps along the way, all these other green points here, they're what we call our nexus points. And so we can automatically generate those. You can see those SDFs if you really want to, but the point is these are aspects where we need a set of conformers that are the generated conformers of the ligand, and we need a set of docked poses that have come from somewhere. And in this case, we could do that from Mo, or we could do that from MTDoc, or you could likely do it from Glide or anywhere else. In all the results I'm going to talk about, these were based on rigid receptor docking, where you had, again, one target conformer, and again, that's the protein conformer, and N-bound ligand conformers. But I could have just as easily performed with certainly with a little bit more time, but just as easily performed an induced fit, which would have had N target conformers and N-bound ligand conformers, or I could, of course, do a dynamic snapshots where it again would be N target and N ligand. Generally, in everything that we're talking about here, that N is 25. Everything we usually do is 25. Yes, very often you can get pretty good results even with just a few really good poses. But what we have seen in our experience is it tends to top out, and 25 is usually a good number that doesn't cost a whole lot to generate, and it doesn't generally hurt you too bad to have a few that are just questionable poses. Here's a rundown in terms of the timing. This is directly from that set. And again, as you can see, you're talking about minutes for the overall MT calculation. And then, of course, then the doc is something that takes as long as it takes. So for the first set, we went down through this comparative set that was, again, out of the PDB bind benchmark. This was 51 sets. 5 X-ray models per enzyme type, and the reason why we wanted to do this benchmark and the subsequent benchmark first was this allows us to compare a single X-ray pose to a set of ensemble docked poses and bring those two together. And so again, this was 51 of them. It also gave us a good idea from a general perspective how well the method's going to do with many different targets and many different ligand cases. You can see here where, again, along the y-axis is the ensemble score versus the end state score, and again, the end state score is performed on the X-ray pose, and the ensemble score is the Mo rigid receptor docked poses. And of course, what we want to see is in a great world, we'd see everything up here in the B quadrant, where again, this is the Pearson R, where everything in the B quadrant is above 0.5 in this case for both X-ray and the ensemble. But we didn't, obviously, you're not going to see necessarily every single one of them. And so we did have a handful of them here that didn't perform as good or as well as we would have liked. But you can see the vast majority of them did. Actually, I believe that was 38 of them did report very well.
Hey, Lance, sorry to interrupt. Just to let you know, we're getting into your 5 minutes Q&A.
Okay.
Okay.
Sounds good. Thanks. And I'm just wrapping up now, so this is perfect. In terms of that, so this is just a quick little breakdown. Then everything in red would be the ones that were in that lower left-hand quadrant. Everything in blue is up in the upper quadrant. Now here's where it gets interesting, though. So we like to see that most of them were up here in this quadrant. But there were a few that end up being in this quadrant. And what this means is the ensemble actually did better than the X-ray poses. Now that could mean that the X-ray pose was just not all that great a pose. Maybe there's something else wrong with it. Crystal structures, as we all know, are certainly imperfect. But in this case, the coverage, the sampling from the docked poses was actually better than the X-ray pose. In this case, they're all very comparable. There's very few that went the other way, and certainly none of them ended up in this lower right-hand quadrant. If you want to look at mean unsigned errors, another metric to be looking at, again, along the y-axis would be these ensemble scores from the rigid receptor docked poses. versus the X-ray poses along the y-axis. And here we see in the vast majority of them were under a kcal of error. Again, really nice to see. If you, again, we want to see this breakdown, all of them in blue were the ones that were less than 1 kcal of error. The ones in red were not. And again, we saw factor 10a, which was also in the previous one, was better for the ensemble. Now, of course, everybody is was likely saying, well, that's great. You did this with 51 sets, but there was only 5 X-ray models per enzyme. What happens when we look at something that may be a little larger? In this case, we did 10 targets with 248 ligands. And you can see again that, that for the most part, a good set of them, most of them were above 0.5, of course, 0.78, 0.83, so on and so forth. And again, in this case, anything that's in blue, that showed the better results, whether it was in the end state or the ensemble, or comparable in the case when they were equal. And so you can see here again, very often the ensemble is as good as or better than the X-ray pose. And that's what we really want to see. That way we know that we can use this methodology in that way. So just a rundown, a very quick rundown in terms of conclusions. The method itself is, it's not like conventional free energy methods, since it doesn't depend upon dynamics. You can use dynamics, but it's not dependent upon it. These results tend to be very comparable to those that have been published from FEP and other methods, but at a lot lower cost. And then finally, it is a very generalizable method. There are cases certainly that it doesn't work, but there are a good number of cases that it does. A lot that's coming up along the way. This is something we can use pretty much any pair-potential we like. We've done it with both Amber and GARF. We are now adding the capability of having parm-top files. If you had we're now adding the capability of reading in trajectory files. So if you wanted, if you'd already done something conventionally, you can do that as well.
I need to finish.
And then in terms of the some overall acknowledgements, I certainly want to thank my group. They've been very supportive of the process. The National Institutes of Health, obviously, for providing a lot of the cash, and then certainly I would say our clients and users. This year has been our you could almost say our launch year, and has been a really good a lot of really good feedback from those beta testers. And of course, I also have to thank you as well.
Okay, thank you so much.